The chapter we're dealing with now is talking about quantum weirdness. And right at the top of the list of quantum weirdness things is the EPR paradox and Bell's theorem. So let's talk about these. We've talked a little bit before about quantum indeterminacy. So even if we know all there is to know, which is the wave function, we can't predict the result of even a simple experiment to measure position. Suppose I measure the position of a particle to be at position x sub I. Where was it prior to the measurement? Well, this is actually controversial. A realist would say it was really at that position and that quantum mechanics is incomplete. We're missing something that would help us be able to predict where the position was. An orthodox, which is also sometimes called the Copenhagen interpretation, would say the particle wasn't anywhere. It was the act of measurement that forced the particle to take a stand. Now, Einstein was never really comfortable with quantum mechanics. He felt, being a realist, that the properties of physical objects have an objective reality independent of measurement. And so, of course, we know in the orthodox interpretation we can't say a quanton that was measured to be, say, spin up had that property before the measurement. It could have been in a superposition. In fact, we only know one spin component of the particle at a time because measurement of one component disturbs knowledge of the others. So Einstein always thought quantum mechanics was incomplete, an incomplete description of reality, and was always trying to come up with sort of paradoxes that would throw off quantum mechanics. And most of the ones he came up with, people were able to figure out, what was wrong with his argument. And today we're going to talk about one, the EPR paradox, which was much more involved. So again, we have these two views, the realist, so there is a such thing as objective reality, and the orthodox Copenhagen, objective reality does not exist. Now, one thing we need to talk about before we actually get into the EPR paradox is what's called locality. And locality, the rough version, it just says only things close to me can affect me. So hopefully that makes sense in general. The more precise special relativity version is no influence may travel faster than the speed of light. So over here we have a space-time diagram, which is something that you can use or will use sometimes in special relativity. And so it's a diagram where we have the x-axis is position, and then the y-axis is time. So little points on this axis are what we call events, and so it's some x comma t. And basically right here in this particular space diagram, so if we assume that maybe I am right here at the center at the here and now, all right, this thing basically shows me what events I could possibly influence. Okay, so we do this in units of position, which is light years, and time, which is years. So light is actually has the slope of 45 degrees when it travels in this space-time diagram. And so basically you look here at event D, I could send some signal slower than light to reach event D, okay, from where I am right now. I cannot send a signal to event C, okay, and so this would be the sort of precise special relativity version of locality. So in 1935, Einstein and two other people, Podolsky and Rosen, came out with the paradox. And in this paradox, you can phrase it a bunch of different ways, but the way we're going to look at it is a way that many people talk about it. Say we have a source of spin 0. So here's our source. So our source has spin 0, and it decays into an electron and a positron. Okay, and so they shoot off. So maybe this is the electron, this is the positron, doesn't really matter. So they shoot off. Now to conserve spin, one must have spin up and one must have spin down in order to keep the spin of 0. All right. Now, and what this means is our quantons, what we call entangled. And so the state vector of these quantons is some linear combination of these two things here. And so this is what we do if we have a state vector that's describing two particles, is we multiply two kets together. And so basically we're looking at the kets, and our two possible states are this. Okay, so so there's basically position A and position B. We have some SG devices, and let's just say that the angles are the same. So let's say that for this instance, theta A equals theta B. And so what that means is if this case is true, all right, if at A I measure the spin of the particle in the z direction to be up, I have to measure it down at B. So that's one possible choice, and the other choice is the opposite. Okay, if I get down at A, I get up at B. All right, and so now the crazy thing is that the state vector for these electrons beforehand, just like other state vectors, is some linear combination, which means that it's in a superposition of these two states. So we don't know ahead of time which one it's going to be. So Einstein argued what this means, if you look at the Copenhagen interpretation, is that if I measure spin up here, all right, and so I collapse the wave functions. That means I collapse the wave function into this particular combination of kets, which means I instantaneously collapse the wave function at B as well, even though B could be many kilometers away. And so there's no way to reconcile this with locality. And so this is the heart of the EPR paradox. And so Einstein argued, okay, so if you measure spin up at A, you're determined to get spin down at B. And so, of course, according to Copenhagen, that means that if it was in a superposition beforehand, you collapse the wave function A while you're collapsing the wave function at B instantaneously. Okay, this cannot be reconciled with locality, and so he thought this was ridiculous. Many people thought this was ridiculous. You might think this is ridiculous. And so he argued that the particle at B must have been spin down all along. Okay, it must have been an element of reality, and that quantum mechanics is just not good enough to predict this. Okay, so it's incomplete. And this was a very strong argument that he had. And so, since we cannot have a non-local influence, the outcomes must be predetermined by objectively real properties. These are things we call hidden variables that each electron carries with it. And so, since quantum mechanics does not describe these properties, it must be incomplete. Now, this was something that Bohr was not really able to argue against Einstein on this. The big issue here is that, the experiment we just described is the results are the same regardless of your interpretation. So there is no way to explain this or to sort of look at this experimentally, at least according to the example we just showed. And so there was arguments, but basically people just decided to agree to disagree on this, and life moved on. All right, so just to recap, so Einstein said, since we cannot have a non-local influence, all right, so since, this idea of things influencing each other instantaneously, he didn't like that. Well, that means that the outcomes of these experiments must be predetermined by some sort of objectively real property of the electrons. And these are what you'll often hear referred to as hidden variables that each electron carries with it. So quantum mechanics is incomplete, and you'll sometimes hear this referred to as a local hidden variable theory. So you may have heard these kind of things thrown around. So again, the hidden variable means there's something that quantum mechanics doesn't know about that actually predetermines these experiments, and local means that it's part of the electron, so it's not being influenced by the other electron. All right, so again, there was no experiment to test between these two interpretations, and so nothing really came of this for many years. And then came along Bell's theorem in 1964. And this theorem says that no physical theory of local hidden variables, okay, so this theory that Einstein just described of some sort of hidden variable, can ever reproduce all of the predictions of quantum mechanics. And so there are specific measurements that can be made to distinguish between quantum mechanics and some sort of local hidden variable theory. And so it's now an experimental question, all right, whether quantum mechanics is incomplete or if the world is inherently non-local. And so what we're going to do now is go through and try to explain one of these experiments. So there's many experiments that Bell's theorem describes, but we're going to try to do one in particular just because it's a little bit easier to understand one than sort of trying to understand all of them at once. All right, so one of the ways to interpret, or at least one of the experiments you can look at in Bell's theorem is this variation here. So it's the same sort of setup we had before. You have a spin zero particle stopping here. It decays into an electron and a positron that are both sent out. and they go to the detectors. And so you have two detectors, and before with the detectors we had them at the same angle, and we just called it Z. But now what we're going to do is we're going to imagine that you can rotate these vectors around. And so here's a picture. Okay, and so imagine that the electron is coming through and sort of coming right into these detectors, like right through here. All right, the detector is set up so you can swing it around between angles of 120 degrees. And we're going to call the three axes 1, 2, and 3. And basically what happens is the experimenters at A and the experimenters at B have these three positions, and they randomly pick one each time the experiment happens. Okay, so this one might, pick 1 and then 3 and then 1 and then 2 and then whatever. And this one randomly picks them too. So they're not coordinated at all. They're just totally done randomly. And then one variation of this, which is how the book describes this, is we set up little lights. And so for experimenter A, if the electron comes out of the positive end, a little red light goes off. If it comes out the negative end, a little green light comes off. And for experimenter B, it's the opposite. If it comes out positive, it's a green light. If it comes out negative, it's a red light. And so what we're going to go through is describe this experiment from the two viewpoints, okay, from a viewpoint of Einstein and then from the viewpoint of a quantum mechanic Copenhagen person. And the thing we're going to focus on are these lights. Okay, so we want to look at whether or not we get the same lights for the two experimenters or different. And so you can imagine that if you just did this experiment, each side, the experimenter would say, okay, we get red, green, green, red, green, green, red, 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 something like that. Okay, and then the other team has a similar list, and what they do is afterwards they come and compare them. And so we want to see what's the probability of getting the same signal or different signals between the two detectors. And we'll find that the realist and the quantum mechanic Copenhagen person get different results in this particular experiment. And that was sort of the genius of Bell's theorem, was finding a set of experiments where you could actually get different results between those two theories. We're going to start by looking at this experiment through the eyes of Einstein and the local hidden variable theories. Okay, so again, the local hidden variable theories say that the results of these experiments are already known when the particles leave the source. And what they say is that basically the particles have what they call instruction sets, which is sort of an unfortunate way to say it. But basically the particles already have or already know what the results are going to be for the three axes 1, 2, and 3. And so the first thing you got to convince yourself that if the angles are the same, so let's just say that theta A equals theta B in this experiment. Okay, then if over here, say that I measure spin up, okay, that means bing, I get a red one. Then over here, I have to measure spin down, again to conserve spin, I get spin 0. So I have to get spin down, and bing, I get red. Okay, and so whenever it's the same angle, I'm always going to get the same light. And so that's why you can basically describe the total experiments in 3 letters. And so basically those 3 letters in our book represent what the light would be in the 1, the 2, or the 3. And so for instance, if we take the one we just did, it would be R, R, R. Okay, and what that basically tells you is that both of the particles, the electron and the positron, would being red if the detectors happen to be at 1. They would flash red if the detectors happen to be at 2, and then red if they happen to be at 3. All right, and so basically there's 1, 2, 3, 4, 5, 6, 7, 8 ways this can be, okay, because basically each one can only be red or green, and there's 3 of them. And so we can just sit down and literally go through these statistics and figure out the probability that both detectors are the same or the opposite. And again, just remember that the one difference would be that if one of them happens to be at a different angle. Right? If they're always at the same angle, we always get the same color, and so the experiment's not very interesting to us. And so let's look here at this clicker question. So here we have a little chart that they do in the book of the instruction sets versus the orientation pairs. And so again, we just talked about what these things are. The orientation pairs, this 111 means that both experimenters just happen to be at the number 1 spot. Okay, this one here means experimenter A happened to be at 2, experimenter B happened to be at 1. And so if we look at these and look at the instruction sets, we can figure out whether the lights are same or different. Okay, so take a second to think about this, and we'll talk about this. Okay, so our instruction set for this particular one is RRG. So let's write that out again, RRG. So that means 1, 2, and 3. So that means if I happen to go at 1 in the experiment, I'm definitely going to get R. If I go 2, I'm going to get R, so on and so forth. And so here, 1 and 3. So one experiment is at 1, one's at 3. So I'm going to have R and a G. And so that's going to be different. 2 and 1 would be 2 and 1. Those are both R, both red. So that's the same. And then 2 and 2, well, that's going to be the same. All right, so hopefully when you did this, you got B as the answer there. Now you can fill in this whole chart, but you know, it's just basically doing that over and over. I mean, if you're still kind of mixed up, maybe fill in a few more. But what they do in this chart is at the end, they write out the probability of being the same. And so, for instance, when the instruction set was RRR, this was always the same, and so it was 100% that you get a probability of being the same. And so now let's look at this next example. So here are the 8 possible combinations of spins, our instruction sets, that result from our decay. So now if we're looking at the hidden variable picture, if we run the experiment with a large number of electrons, what is the hidden variable probability of getting different? And so in this chart, we write it out here that basically this probability is 1 to get the same, this probability is 1 to get the same, and it works out that these 6 in the middle, the probability of getting the same is 5/9. So what's the probability of getting different? So think about this one and we'll talk about it. All right, well, hopefully for this one, you got that it's less than or equal to 4/9. And so if you look here, so again, what's happening is when you shoot off these electrons, we assume that which one of these the electron and positron comes out with is randomly assigned. So basically each one has 1/8 probability of happening. Well, for these ones in the middle here, okay, it works out that it's 5/9 probability of each of those to be the same. And of course, how does that add up? Well, if you just look here, there's 1, 2, 3, 4, 5 sames, and there's a total of 9 possibilities, so it's 5/9. So what's the probability of being different? Well, for all of these ones, it's going to be 4/9 probability. And so if you only happen to send, you know, ones in that little box, those 6, the probability will be 4/9 of being different. However, when you once in a while, okay, you know, 2/8 of the time send one from the RRR or the GGG instruction set, that's going to be 0% chance of being different, and so that's why it's less than. So depending on how many of those you send. Okay, but basically the maximum it can be is 4/9, and then more than likely it'll be something a little bit less than that. And so again, this is the probability of either being the same or different according to the hidden variable. And we're going to show now that according to traditional quantum mechanics, it's a different probability. All right, and just to recap for the local hidden variable theory, the probabilities of being different are maximum of 4/9, probably less than that. The probability the same, minimum of 5/9, probably bigger than that. And so no matter how one adjusts the populations, the results will have to be consistent with these inequalities. Now looking at this just quantum mechanically, we can calculate probabilities and we find that they're different. And so basically if we do this, there's 2 possibilities in this experiment. Okay, the first 2 is that the axis the experimenter picks is the same, and the second one is that the axis that the 2 experimenters pick are 120 degrees off of each other. And we're going to find it doesn't matter if we're 120 by doing like this one and this one, or if we're 120 by doing, say, this one and this one. The results are going to be the same. And so we can really just boil this down to 2 cases. Okay, so the first case, if the 2 axes happen to be the same, so for example, let's say that theta A is 0 and theta B is 0, okay, what results will we have? Will the 2 lights be the same, different, or does it depend? So think about this one and we'll talk about it. Okay, hopefully you got that they're the same. If it's the same axis, then that means if I get red, which means spin up, I have to get spin down over here, which means red. So they're always going to be the same if we happen to pick the same angle. Now, The other case, where they're 120 degrees off from each other, is a little bit trickier. Okay, so let's just say that we did this experiment and the detector at A is in the Z direction and the detector at B is 120 degrees off from this. Okay, so now suppose you measure spin up at A right before the measurement of B is made. So say, for instance, that A is just a little tiny bit closer than B. Okay, and so I measure A and I get spin up. Now what that means is I've, at least according to Copenhagen, is that I've collapsed the wave function of my particle over here. And so if this one is spin up on this side, okay, what is the spin state vector at B before a measurement is made? So think about this one and we'll talk about it. Okay, hopefully you got D, right? Now that we're just here, we're not talking about what B measures, we're talking about just the state vector. And again, we're sort of making this assumption that A was a little bit closer. So once you measured spin up over here and got this red, all right, over here what had to happen is you had to be spin down in the Z direction. That's your state vector for that electron before it enters this device. Okay, so pause right here and make sure this makes sense. I think this is a really tricky idea. If it doesn't quite make sense, or ask questions on the pre-class questions. All right, and so our last clicker question. So again, it's the same setup. All right, so we're assuming that this thing SG theta A is at angle 0. And this theta B is 120. And remember this thing, so it came out as a positive Z, and so that means we got the red light with that one. And so the question is, what is the probability you will get a same result? So the same light, the red one, will flash over here. And as a hint, I've given you this state vector, negative theta. So think about this one, and we'll talk about it. All right, so we know from the last problem that coming in to SG theta B, I had to be a negative Z electron because I got positive Z over here, which means I have to have negative Z over here. Now, you know, this is not measuring in the Z direction, it's measuring 120 degrees off of that. And what I want to do is I want to find the probability that it gets negative theta. And so basically I want to find the inner product of negative 120 with my negative Z. All right, so that's the inner product that if I start in the negative Z, I'm measured to be down here in the negative theta, negative 120. All right, and so that's why I gave us this one over here. And so we do this, negative sine of the theta will be negative sine of 60. And then cosine of 60 for that vector. And then of course it's 0, 1. And so my inner product will be cosine of 60. You square that, and the probability will be cosine squared of 120 divided by 2, which I just kept that way just so it was a little bit easier to see, I think. All right, so again, these probabilities are really, I think, kind of hard to make sure you got it. So I would stop and think about this, and again, ask me questions if you have any. But once we have that, okay, so what happens is the total probability, if we look at just pure quantum mechanics, of being the same. All right, so what's going to happen is a third of the time I'm going to be in the exact same direction as the other experimenter. So A and B will be aligned, and if they're aligned, you always get the same color. If they're not aligned, we just saw that cosine squared of 60 is the probability that the lights will come out to be the same. And that's going to happen 2/3 of the time if you just sort of randomly pick the directions. And so if you add all this together, you get that the probability of being the same is 1/2. Now, you want to kind of prove that it's 1/2 to be different. I mean, it should be. And so you think about, well, the probability cosine squared of 60 is the probability you get the same light when they're misaligned. And so sine squared of 60 would be the probability you get different lights when they're misaligned. And again, that happens 2/3 of the time, and you get 1/2. All right, and so basically the probabilities in quantum mechanics of this experiment should come out to be 50%, either different or the same, whereas that was different than what happened if you looked at the local hidden variable theory. So these predictions are inconsistent, so it's now an experimental question. And so these type of experiments have been carried out and consistently agree with the predictions of quantum mechanics and thus seem to rule out a local hidden variable theory. What this means is quantum mechanics is inherently non-local. So this weird business of collapsing a wave function that could be many kilometers away from you seems to be an aspect of quantum mechanics. In fact, these non-localities are at the foundations of things like quantum information and quantum computing. And so you can ask yourself this question: how can measuring A collapse the wave function at B? Doesn't this violate relativity? And it is definitely really weird and does not necessarily make you feel good. But one thing you can grab a hold of is no, because you can't really send information via this collapse. And so this is one thing to think about and ask me questions if you can't resolve this. Okay, and we'll talk more about this and some other quantum weirdnesses coming up in class.